The illusion of space telescopes. You've probably seen those images. They appear suddenly, spreading across the internet in waves of galaxies painted in unreal colors. Nebulae so sharp they seem almost artificial. Ancient light, frozen in breathtaking detail. The James Webb Space Telescope has become a symbol of progress, of discovery, of humanity's reach into the deepest darkness, and slowly, almost imperceptibly, a belief is formed that if we want to understand the universe, we must look to space above the atmosphere, above clouds and turbulence, above the limits of Earth itself. From orbit, everything seems clearer, cleaner, more absolute. For a moment, this idea feels complete, but this picture hides something important that quietly reshapes how we think about astronomy, about where real discovery happens, about what kinds of questions we are still able to ask, because while our attention has been fixed upward, while space telescopes have captured the spotlight, something else has been taking shape, quietly, deliberately, on the ground. For decades, astronomy followed a simple story. First came giant ground-based telescopes. Then came space observatories. Hubble changed everything. Webb pushed even further, and so it seemed logical to assume ground telescopes were the past. Space telescopes were the future. A clean, technological progression. But the universe does not care about clean narratives. Astronomy is not only about clarity. It is about scale, about repetition, about watching the same sky again and again and again. Most cosmic events do not reveal themselves in a single image. Stars brighten and fade. Asteroids drift silently through darkness. Explosions appear where nothing existed before. To understand the universe, we don't just need snapshots. We need time. Space telescopes are extraordinary, but they are rare. Each observation is precious, each target carefully chosen. They are perfect for detail, but not for constant watching. They cannot scan the entire sky, night after night, for years, and that limitation matters, because the universe does not wait. Change happens whether we are watching or not. For a long time, astronomy had to choose depth or coverage, precision or persistence, but that trade-off is beginning to disappear. Not in orbit, not in space. On Earth, far from city lights, in one of the harshest deserts on the planet. A new observatory was built, not to compete with space telescopes, but to do what they cannot. To watch everything, all the time. In the next part, we leave orbit behind. We travel to a place where the future of astronomy is firmly anchored to the ground, and we discover why the next revolution was never meant to float above Earth, but to stand on it. Where the ground becomes an advantage. To understand why the ground still matters, we need to change perspective, not upward, toward orbit, but downward, toward Earth itself. At first glance, the idea seems counterintuitive. Earth's atmosphere distorts light. Clouds interrupt observations. Airglow and light pollution contaminate the night sky. Compared to space, the ground appears flawed, imperfect. For decades, astronomers worked around these limitations, correcting, compensating, adapting. And for a long time, it felt like a losing battle. But Earth has something space does not. It has stability. Space telescopes move at thousands of kilometers per hour. They age under radiation. They rely on limited fuel. They cannot be easily repaired. A ground-based observatory, by contrast, can be upgraded, expanded, recalibrated. It can evolve. And when it is placed in the right environment, its disadvantages begin to fade. That environment is rare, extremely rare. Only a handful of places on Earth offer conditions close to ideal for astronomy. High altitude, dry air, minimal cloud cover, stable atmospheric layers. One of the best of these places lies in northern Chile. The Atacama Desert is not just wide. It is one of the driest places on the planet. Some regions receive less rainfall than parts of Mars. At high elevations, the air becomes thin and steady. Moisture, the enemy of clarity, is almost non-existent and far from cities. The night sky remains dark, truly dark. This is where the Vera Rubin Observatory stands, not hidden, not isolated, but deliberately placed where Earth itself becomes an advantage. Yet location alone is not enough. Even in perfect conditions, A telescope must be designed for its mission, and Rubin's mission is fundamentally different. Most telescopes are built to look deep. They focus on a single target. They stare. They gather photons patiently, extracting detail from darkness. Rubin was built to move. To scan. To repeat. To return over and over again instead of asking, what is the most detailed image we can capture? Rubin asks a different question: what is changing right now? This shift changes everything, because the universe is not static. Stars pulse. Galaxies interact. Asteroids pass silently through our neighborhood. Some events last seconds. Others unfold over days. Many are never repeated that if you are not watching at the right moment. They are gone. For most of astronomical history, we relied on luck. A supernova happened to appear in the field of view. An asteroid happened to be noticed. A flare happened to be observed. Rubin removes luck from the equation. By scanning the entire visible sky every few nights, it creates a baseline. A reference. Anything that changes stands out immediately. Anything that moves, brightens, fades, or appears for the first time is flagged automatically. This is why ground-based observation matters again, not despite Earth, but because of it, because only from the ground can we build something large enough, flexible enough, and persistent enough to watch the sky continuously for years. In the next part, we move closer. We look at the machine itself, the mirrors, the optics, and the design choices that make this observatory unlike anything built before. A telescope built for a different question to understand why the Vera Rubin Observatory is so different. We need to forget what we think a telescope is supposed to do. Most telescopes are designed around a single idea: look deeper. They narrow their focus. They zoom in. They collect faint light from one small region of the sky and turn it into detail. That approach has given us extraordinary discoveries. But it comes with a trade-off. The deeper you look, the less of the sky you see. Rubin was never meant to win that race. IT was built to answer a different question, not what is farthest, but what is happening right now. This difference shaped every design choice, from the mirrors, to the camera, to the way the telescope moves. Rubin is not a patient observer. IT is restless. Instead of staring at a single target for hours, it sweeps across the sky, exposure after exposure, night after night, returning to the same regions again and again and again. Each visit is brief, but together they form something powerful. A record of change. This idea is simple in principle, but extremely difficult in practice. To scan the entire visible sky repeatedly. A telescope must be fast, not just in how it moves, but in how it gathers and processes light. It must maintain sharp focus across a huge field of view, and it must do so without sacrificing image quality. That requirement led to a radical optical design. Rubin does not rely on a traditional two-mirror system. Instead, it uses three mirrors, carefully shaped and aligned. The primary mirror collects light, the secondary redirects it, and the third corrects distortions across the field. This allows Rubin to maintain clarity from edge to edge of each image. No soft corners, no warped stars, just consistency. This may sound technical, but its impact is profound. Most telescopes deliver their best performance only at the center of the image. Rubin delivers it everywhere, which means no part of the sky is treated as secondary. The telescope itself is massive, but it moves with precision. It can reposition rapidly, settling into place with remarkable accuracy. This speed is essential because Rubin does not take one image per night. It takes thousands. Each observation follows a rhythm: point, expose, move, repeat. The cadence is relentless, and over time, this rhythm builds a map of the sky that is not static, but alive. This is what sets Rubin apart. It does not ask astronomers to choose what is important. It records everything and lets change reveal itself. Anything unusual stands out. Anything new is noticed. Anything fleeting is captured. This approach transforms astronomy from a reactive science into a proactive one. Instead of waiting for discoveries, Rubin creates the conditions where discoveries cannot hide. In the next part, we'll look at the heart of this system, the camera, the largest digital eye ever turned toward the sky, and why its scale changes not just how we see the universe, but how much of it we can see at once. The largest digital eye ever built at the center of the Vera Rubin Observatory is something no telescope had ever carried before, not just a detector. Not just a sensor, but an eye. A digital eye so large that it redefines what an astronomical image can be. This camera is not an accessory. It is the core of the entire project. Everything else, the mirrors, the mount, the control systems, exists to feed light into IT.in size alone. It is unprecedented, roughly the size of a small car, nearly 3 meters long, more than 1.5 meters wide, and weighing close to 3 tons. This is not something you casually attach to the end of a telescope. It required an entirely new engineering approach inside. This massive structure are 189 individual imaging sensors, each one precisely aligned, each one cooled and stabilized, each one synchronized with the rest. Together, they form a single detector with a resolution of 3.2 billion pixels, 3.2 gigapixels. To put that into perspective, a modern smartphone camera captures around 12 million pixels. This camera captures nearly 300 times more. In a single exposure if you wanted to display one Rubin image at full resolution. Without downscaling, you would need approximately 385 4K screens, side by side, just to see it all at once, and yet, resolution alone is not the point. What truly matters is how much sky fits into one frame. Each Rubin exposure covers about 10 square degrees of sky. That is an enormous area. For comparison, the full moon occupies about half a square degree. Rubin captures an area roughly 20 times larger than the moon in a single shot. This wide field of view is not an accident. It is the foundation of Rubin's mission, because to watch the sky change, you must see a lot of it all the time. The camera is designed to detect light across a broad range of wavelengths, from ultraviolet through visible light and into the near-infrared. This allows astronomers to study not just shapes and positions, but physical properties, temperature, composition, distance. To achieve this, the camera uses a complex filter system. Massive optical filters, each weighing hundreds of kilograms, are moved in and out of the light path with extreme precision. Each filter reveals a different layer of information, but capturing light is only half the challenge. The other half is what happens next. Every exposure produces an enormous amount of data, not just pixels, but timestamps, calibration information, and metadata. All of it must be processed almost immediately, because Rubin does not wait. The telescope moves on, the next exposure begins, and the data stream never stops. In a single night, the observatory can generate around 20 terabytes of data night after night for 10 years. This is not just an observing program. It is a data engine handling this flood of information. Required building an entirely new data pipeline. Images are processed automatically, compared against previous observations. Differences are detected in real time. Anything that changes is flagged within minutes. This speed matters, because some cosmic events are short-lived. A supernova in its earliest moments, a near-Earth asteroid passing quickly, a sudden flare from a distant galaxy. If you miss them, they are gone. Rubin is designed not to miss them. The camera scale, its sensitivity, and its speed combine into something new, not just a tool for imaging, but a machine for discovery. In the next part, we'll see what happens when this digital eye is turned fully toward the sky, the first images, the first detections, and why they are only a hint of what is still to come. A living universe. What Rubin ultimately changes. The first images from the Vera Rubin Observatory were never meant to impress. They were not designed for headlines, not crafted for beauty, not composed for emotion. They were tests, quiet checks of optics, sensors, timing, and calibration. And yet, even in those first frames, it became clear that something fundamental had changed. Because Rubin does not show us a frozen universe, it shows us a living one. 4 centuries. Astronomy was built on stillness. We captured moments. Single exposures. Timeless snapshots of distant objects. Stars looked eternal. Galaxies seemed fixed. The sky felt permanent, but permanence was an illusion. In reality, everything moves. Everything changes. Stars brighten and fade. Galaxies collide. Asteroids drift silently through the dark. Explosions flare and vanish in days. The universe is restless, and Rubin was built to watch it breathe. Unlike telescopes that focus deeply on a single object, Rubin looks outward wide. Fast, relentless. It scans the entire visible southern sky again and again every few nights for 10 years. This repetition is not redundancy. It is revelation. By comparing each new image with the ones taken before, Rubin turns change itself into data. Anything that moves, anything that brightens, anything that appears or disappears, nothing escapes unnoticed. This transforms astronomy. Instead of asking what is out there, we can finally ask what is happening right now. Supernovae will be caught in their earliest moments, not days later. But hours after ignition, asteroids will be tracked before they pass unnoticed. Variable stars will map the true structure of our galaxy, and rare, unpredictable events, the kinds we didn't even know to look for, will announce themselves. Automatically, but perhaps the greatest. Impact will be quieter, more subtle. Rubin will collect more optical data than all previous observatories. Combined. By orders of magnitude, patterns will emerge where none were visible before. Statistical truths hidden inside billions of objects will finally become clear. Dark matter will reveal itself not through direct detection, but through its gravitational fingerprints. Dark energy will be constrained by watching how the universe stretches over time, and crucially, this knowledge will not be locked away. Rubin's data will be shared, images released, alerts published, discoveries distributed across the world. Professional astronomers, students, citizen scientists, and algorithms yet to be written will all explore the same sky. This is not just a telescope. It is an archive of time. A record of how the universe changes night by night, year by year. One day, long after the survey ends, astronomers will return to Rubin's data to answer questions we haven't thought to ask yet. They will rewind the sky, replay the past, and discover that their answers were already there. Because for the first time, we are not merely observing the cosmos. We are watching it unfold, and somewhere in that endless stream of light, among billions of stars and galaxies, the universe is already preparing its next surprise.